プレゼンテーション3、電源色素増感太陽電池の高性能化を目指して、植物から抽出されるアントシアニンの活用。愛知県立令和高等学校の皆さんです。浦野春之さん、坂田風太さん、庄地修さん、伊藤春菜さん、石山悟さん、加藤大河さん、玉木祐介さん。指導は大岩真也先生、山田哲也先生です。それではよろしくお願いします。
We are Urano, Sochi, and Ito from Reiwa Senior High School. We are aiming to improve the performance of dye-sensitized solar cells, or DSCs, using anthocyanin pigments which are extracted from plants. I'll talk about the motivation of our research. DSCs can be made at a relatively low price. But if we use expensive pigments like synthetic pigments to generate more electricity, this advantage would be lost. Therefore, we tried making cheaper solar cells by using anthocyanin. There are three objectives of our research. First is examining which structure of anthocyanin is suitable for DSCs. Second is examining the effect of saccharide and impurities contained in the extracted solution. And the last is examining which particle size and film thickness of titanium dioxide are suitable. We extracted anthocyanin from eggplants and black carrots. These are the structural formula of nasmin, anthocyanin contained in eggplants. The anthocyanin of nasmin is called delphingin, and 3 hydroxyl groups are combined with pyrene. And saccharide is combined with position 5 of arine and position 3 of serine. And organic acid is combined with the end of the saccharide combined with position 3 of serine. These are the structure of black carrot anthocyanin. Its anthocyanin is cyanine, and 2 hydroxyl groups are combined with pyrene. Saccharide and organic acid is combined with position 3 of serine. The way of extracting and refining anthocyanin is almost the same as previous studies, so I'll explain it briefly. This is a procedure for the extraction. We extracted anthocyanin with formic acid methanol water. This is a procedure for the refinement. We refine the extracted solution with an amber-like X80 resin and solidified anthocyanin. It turned out that black carrots include 4 times as much anthocyanin as eggplants.
Next, I'll explain how to make a DSC. To make cathodes, we used to apply graphite or pencil to connect the glass, but from the result of our experiment, we found that we could attach suitable candles more uniformly than graphite, and the performance of DSC improves when we use it. So we attached the soot. We made an anode through the squeegee method in the same way as previous studies. We dissolved the potassium iodide and iodine in ethylene glycol to make electrolyte. Next, I'll explain how we evaluate the performance of DSC. We irradiate the light of projector on DSC and conduct the measurement connecting it to this circuit. We measure the voltage value and current value, changing the resistance. We connect the IV measure based on short circuit current density, open circuit voltage, and reflector to evaluate the performance. We repeated 3 times and took the average. We used to conduct manual measurement using a breadboard, and difference of IV characteristics was large, but the measurement equipment is expensive, so we use self-built automatic carbon register switching device. This is the circuit diagram of the device. This device is controlled by this part, microcontroller. The microcontroller is the program to the switch the resistor to one with lower resistance. Each of 15 resistors of circuit A has different resistance between 10 kilo ohm to 0 ohm. resistance value varies when the microcontroller switch is circuit A on or off. This is a diagram of the circuit A. When electricity flows from the microcontroller into the base of transistor, the transistor conducts electricity from the collector to the emitter. Since voltage is applied to relays electromagnets, current flows through one of them, and the resistor is connected to the cell. This is the device. We found that measurement using a device provides a smaller difference of IV characteristics than the manual ones. Next, I'll explain the experiment. In experiment 1, we compare the performance of DSCs with refined extracts and that with unrefined extracts. We use the anthocyanin extracted from eggplants and black carrots, titanium dioxide of 200 nanometer in particle size, and formic acid water as a solvent of pigment. These are the results. First, anthocyanin in black carrots showed higher performance than in eggplant, and the unrefined anthocyanin in black carrots showed a higher performance than refined one. We assume that this is because the extracted solution of black carrots contains more saccharide than in eggplants, and discoloration is suppressed by the saccharide. As for black carrots, saccharide is removed by refinement, and the reaction of hydration more likely to occur, and the color fades.
Next, in experiment 2, we attempt to solidify anthocyanin, the basic structure of anthocyanin. Anthocyanin is usually combined with saccharide, and anthocyanin combined with organic acid is called acylated anthocyanin. Anthocyanin characterizes for the color of anthocyanin, functioning as chromophore. By hydrolyzing anthocyanin in hydrochloric acid, as the figure shows, the bond between saccharide and organic acid is broken, and anthocyanin forms into anthocyanin. I'll explain the procedure. First, we dissolved anthocyanin after refinement in 6-4 hydrochloric acid and heat it at 60 degrees for 5 hours to hydrolyze anthocyanin. And then we diluted it with about 2.5 the amount of water so that anthocyanin would deposit. After filtering it, we diluted anthocyanin in 5% formic acid methanol and dried it in a vacuum desiccator and got solid anthocyanin. From the result of a calculation to find the purity of anthocyanin, it turned out the purity of anthocyanin was lower than that of unhydrolyzed one. This is because some anthocyanin didn't decompose into anthocyanin completely. Next, we compared the absorption wavelengths of anthocyanin before hydrolysis and after hydrolysis. This is the absorption wavelengths of black carrots. The absorption maximum wavelengths at visible light region is responsible for anthocyanin, and they have no difference between them. Absorption maximum wavelengths at ultraviolet region is responsible for organic acid combined with anthocyanin, and acylated anthocyanin shows 2 absorption maximums. On the other hand, anthocyanin after hydrolysis doesn't show its absorption maximum between 350 nanometers and 335 nanometers. So it can be said that we succeeded in making the acylated anthocyanin. Next, in the same way, we compare them in the case of eggplants. But the absorbance of eggplants before hydrolysis was too high. So we changed the density so that we could read the absorption maximum. Like black carrot, the absorption maximum wavelengths at the ultraviolet region was lost. So we assumed it decomposed into the acylated anthocyanin. And finally, we examined the discoloration of anthocyanin. It turned out by leaving pigment for 1 day and measuring absorption again, it turned out that the color of anthocyanin was faded, while there wasn't so much change in the color of anthocyanin before hydrolysis. So it can be said that the structure of anthocyanin is unstable in solution. We made it possible to inhibit the discoloration and preserve the anthocyanin by solidifying anthocyanin. In experiment 3, we compared the performance of DSCs using anthocyanin before hydrolysis and after hydrolysis. We used titanium dioxide of 6 nanometer in particle size and formic acid methanol as a solvent of pigment. These are the results. Unsigning before hydrolysis both shows higher performance than hydrolyzed one. And as a result from experiment, the discoloration is more likely to occur after hydrolysis, and this affects performance of DSTs. We assume that the cause of the discoloration is that the molecule of unsigning would be without surrounded by saccharide and organic acid and readily changes structure by hydrolysis. Next, in experiment 4, we examine which particle size and thickness of titanium dioxide are suitable for one. The condition of particle size and thickness is as follows. We use as a solvent of refined unsigning of wet plants, formic acid water, and conductive measurements. We define the side irradiated by light as absorbing layer, and opposite side as scattering layer. These are the results. Particle 6 nanometer in size shows high pull factor, and particle 200 nanometer in size shows high current value. The one which particle 200 nanometer in size and particle 6 nanometer in size shows the highest performance. This is because the layer of 6 nanometers with much pigment absorbs the much light. And the layer of 200 nanometers scatters the rest of the light. And then the layer of 6 nanometers absorbs the light again. We assume this is the cause of the improvement in the performance.
The conclusion is as follows. Saccharide, which is included in the extracted solution, has a good influence on the performance of DACs. Organic acid protects the anthocyanin from being discolored. The perspective is as follows. As an acknowledgement, we'd like to thank Professor Yoshida and Mr. Kimura, Nagoya University. The bibliography is as follows. Thank you for listening.
ありがとうございました。それではこれよりご質問をお受けしたいと思います。ご質問のある方、挙手をお願いいたします。はい、ではマイクをお持ちいたします。お願いいたします。
So, your experiments and the presentation went up very well. My question is, how much eggplants or black carrots did you buy at the store for your experiments? I think a black carrot could be expensive, isn't it? No.
Thank you for your nice questions. Black carrots we can buy black carrots about 100 yen per 100 gram. So it is easy to get and very reasonable.
And how much amount did you buy for carrots? I think you went to the store, right?
I bought a black carrots about 2 kilograms. And this is extracted volume of one staining per 100 grams. Sorry, I couldn't answer your question in English. So please tell me Japanese.
どれぐらいの、おナスと黒人参を使いました？
私たちは、ここに示してある通り、その 100g あたりのそのアントシアニン量が、どれぐらい取れるかというその量はここに示した通りで、私たちが、その DSC の色素として使っているそのアントシアニンの量は、約、1回のこの DSC3 枚を作る実験で、約 0.01g の、アントシアニンを使用しています。なので、かなりその安価で、 安価で手に入れやすいもので、作成しています。
ありがとうございます。ここはまたご質問のある方いらっしゃいますでしょうか。ではお時間の方も参りましたので以上とさせていただきたいと思います。愛知県立令和高等学校の皆さんでした。ありがとうございました。